This is lecture 9 for chapter 5 of Calculus 3, and in this lecture I'll discuss a piecewise path example of a line integral. In this example, I'm going to calculate the circulation around the top half of a washer. So what we're looking for are the tangential components of the vector field along this closed path. As usual, we're going to assume that there's a parameterization for the top half of this washer, and that in this parameterization the path around the top half is continuous and it's traversed only once, and that the first derivative, continuous first derivative, exists. In the previous examples the paths were easier because they only required one parameterization. This is going to require more. So in order to do the integral, we break it up into pieces. So here's what we're talking about. We have the top half of the washer way out here, R1. Okay, the outer curve of this top half of the washer, and here's the parameterization for that. You see it's out at 2, has a radius of 2. The inner radius of the washer is 1, and here's its parameterization. Then we have two sections here, straight sections, and those are just lines. Okay, so that's 1. Here is 2. Can't really see that well. Here's 3 and here's 4. Okay, that's a parameterization. You see, we already broke it up into 4 pieces. The rest is fairly obvious. So what we're going to do is take the line integral for the circulation. This is the line integral that integrates the tangential component of the vector field around that path, around the outside of this half of washer, and we break it up into 4 other integrals, each along their own paths. Here is R1, R2, R3, and R4. So this will be the function x squared I plus y squared j, and I'll show you what we do with it. So these steps are pretty straightforward, and it's just another example of how to do these line integrals. First thing you have to do is compose the vector field with each section of the path, with the parameterization of each section of the path. So f composed with R1, f composed with R2, f composed with R3, and f composed with R4. You need those 4. Then you need the first derivative of each piece of the parameterization. So that's, of course, just given, whoa, I want to draw on there. It's given right here. And now you take the dot product between these two. Okay, and that becomes the integrand for each integral. Now the only real trick is making sure that you go around the integral as though you're completely traversing that integral. You don't do one section in one direction and then go back and do another section in the other direction. That will give you sign errors and then you get the wrong answer. Okay, so let me try to draw that and I'll show you. All this is done in the limits of integration. Everything else is straightforward. Okay, so we've got, here's the washer. Okay, this was R2 and this was R4. I set it up so that I was going from here to here in that direction, and I want to go R4 in this direction. Now R1 starts here and walks around the outside of this washer, so I'm going to integrate from 0 here to 2 pi over here. Now when I come back, I want to go in this direction, pick up this piece. So I pick this up by integrating from pi to 2 pi. This is lecture 9 for chapter 5 of Calculus 3. In this lecture I'll give the example of a piecewise path line integral of a vector field. In the previous examples the paths were fairly simple so that they could be parameterized by just one function. In this case it's going to require 4 functions to parameterize this top half of a washer. And we'll look at the circulation around it. Could look at the flux, but we'll just look at the circulation. The importance here is how to break up the parameterization to go over the whole top half of the washer. something that's important is that the parameterization must be continuous, and the path must be traversed only once, and the whole thing must be gone over in a counterclockwise direction. You can't do some little sections clockwise and some other sections counterclockwise. So here is the top half of the washer. The outer radius is 2, the inner radius of the washer is 1. So what we do is we break this up into 4 parameterizations. R1, R2 is down here, R3, and R4. So for R1, it's just 2 cosine t, 2 sine t, and let t go up between 0 and pi, and that will trace out this outer curve on the outside of the washer. Now for the next, we need to move from this point here, whoops, find the other pin. So we're going to move from this point to this point. See, we're going to go over here like this. Then we have to come back here in this direction. So we're going to go from -2 and move back over here to 1. Okay. Now, for the lower half of the circle, we need to go in this direction, but the limits of integration are going to be between pi and 0, but we're going to go, instead of integrating from 0 to pi. Oh, that looks wrong. Okay, 0 less than or equal to t less than or equal to pi. I think that's the usual way things go. 0 is less than pi. At any rate, we're going to integrate not from 0 to pi, because that would carry us in this direction. We're going to integrate from pi to 0 in order to go in this direction. That's really the only trick here. Then, in this case, we're going to go from 1 out to here, and the way we set it up, we'll just let t go from 0 to 1 in this section and 0 to 1 in this section as well. So this is the basis right here. This is the integral for the circulation around that top half of the washer, but there is not a single parameterization that can hold the whole thing, so we break it up into 4 parameterizations. That gives us 4 integrals. Let's look at a fluid with this kind of velocity, x squared in the I direction plus y squared in the j direction. And now this calculation is now, at this point, just a straightforward example, or actually 4 examples in one, of a line integral of a vector field in the tangential direction to compute the circulation. First thing we do is compose the vector field with the parameterization in each section. So f composed with r1, f composed with r2, etc. We're going to use those. Then we need the time derivative of each parameterization. That's what we have here. Then we take the dot product between these two, okay, and that gives us the integrand for the integrals. Okay, and here those are right in this section. So that's the same thing we did before, except we have to do it 4 times for this one integral. And now we just integrate, and it's everything's straightforward except the third one. And see, we're integrating from pi to 0, so that we're going, in case you missed that, we're going to go around the top of the washer this way. That's why we're integrating from 0 to pi. Then we set this up, so we just have to go from 0 to 1 here in order to move in this direction. Over here, we set this up, so we only have to go from 0 to 1. If you set this up differently, the r vector for r2 and r4, you might have to integrate from 1 to 0. But now the inside is a problem, or issue, whatever, and it's like this. But if we integrate from 0 to pi, then we'll go clockwise, but we want to keep this counterclockwise direction going, so we integrate from pi to 0. That's what we do here. The integrals are easy. So the only thing I'm showing you is that you can take your object, break it up into smaller parameterizations, apply everything as before to each parameterization, and add the results. Be sure to check your limits of integration and the way you set up the function so that you are continually going around that path in a counterclockwise direction.